Recently, we've entered into the world of continuous random variables, and these are random variables that whose values are on the number line on an interval, negative infinity to infinity, and we've been particularly studying the normal random variable, aka the Gaussian distribution. So Gaussian distribution is synonymous with normal random variable. And there's many things, a lot of characteristics about this particular random variable. We discussed its PDF, has a very distinct PDF, probability density function. And it's of this form, 1 over the square root of 2 pi sigma multiplied by e to the negative x minus mu squared all over 2 sigma squared. And of course, this is for my x values are between positive infinity and negative infinity. Okay, so this is our PDF for the normal random variable. And we also showed that if you take the integral from negative infinity to infinity of our function, of our PDF, this equals 1, right? We talked about that. We also, the graph of the PDF is a bell-shaped curve. It's a very symmetric curve where the middle is the mean, which is mu. The mean, the expected value, the average. And as we move to the right, these tick marks by the standard deviation. And we go all the way to the third standard deviation to the right, and we do the same thing to the left. And then we also talk briefly, so this is a bell-shaped curve, right? So the bell-shaped curve of the normal random variable PDF. So far, so good. So this is what we've been talking about, particularly last lecture, last week. So we talked about the PDF. We showed that it's an appropriate PDF because if you apply the integration, it equals 1. The graph itself is a very beautiful, symmetric, bell-shaped curve. So the word bell-shaped curve is associated also with normal random variable. And we also have certain parameters. There's certain parameters for the normal random variable. So the first one is the expected value. The expected value, so if I call my random variable x, the expected value of x is mu, is that that constant mu. And the standard deviation of my random variable is the constant sigma, little sigma, lowercase sigma. Okay. Okay. So after we've learned about all of that, we also touched upon a few things extra. Every time we learn about a new random variable, we discuss, particularly in the world of continuous random variables, we discuss the probability density function. We show that the PDF is equal to 1. We try to have understanding of what the graph of the PDF looks like. We try to figure out what the parameters are. And then what follows is the CDF. The CDF. And just remember that the CDF is the probability that my X value is less than a particular X value. We're accumulating all of the probabilities up until a particular X value for the random variable. So the idea is that when you have, and of course this will equal the negative infinity to X of f of X dx, right? That's what that means. That's what the CDF means in the world of uh, continuous random variables. So if I have a random PDF, normal random variable, and I have the mu, and I have mu plus sigma, I got mu plus 2 sigma, and so on. What happens is I sometimes want to find this region here, this area, and remember I've discussed this in other random variables. The area, when we talked about uniform random variable, the area now becomes synonymous with probability. And we're going to be interested with these particular kinds of questions. So this area here will be the CDF, or in other words, the probability that my X value is less than X, which is equal to the area underneath the curve. That's what the integration of a particular function gives us. And you know what? Let me change these values here with some other dummy variable. Let's call it f of a dA. Again, this is just for notation's sake. So this here is going to be f of, let's call it a dA. Now, the problem is when we integrate, as you can tell, as you from the previous lecture, integrating this function is kind of complicated, complex. You have an exponential function, and the argument of the exponential function is some variable squared. So the techniques that we have at this moment for integration is quite limited to be able to always integrate this, which we can, but it's very taxing. So what do we do instead? Instead of having to integrate this by hand and all of that? Well, we first discuss what's called the standard normal random variable. Now, what's the difference? What is so special about standard? Well, there's a lot of things that come from just doing two things with the parameters. So the PDF, so the moment I'm talking about standard, the PDF transforms itself into this. The PDF of a standard normal random variable looks like this. It's 1 over the square root of 2 pi e to the negative x squared divided by 2. That's what the PDF is. And why is that? Well, the reason why it's called standard is because my parameters are quote unquote standardized. What are my parameters? The mean is 0 and the standard deviation is 1. This is what makes a standard normal random variable. And the idea is that every normal random variable with parameters, mean with the mean and with a given standard deviation can always be quote unquote normalized or standardized into this particular standard random variable, standard normal random variable where the mean is 0 and the standard deviation is 1. So the graph of this PDF is exactly the same. It's the same bell curve. It's just that the x-axis here is standardized. It becomes, instead of mu, calling it some mu, it becomes 0. The standard deviation is 1, so everything differs by 1. All these tick marks that we have. So we're going to take every normal random variable and standardize it, making the parameters 0 and the standard deviation 1. And we normally denote the standard normal random variable, we denote it with z, the capital letter z. So denoted by z. Okay. And the CDF, we use this little symbol here to denote the CDF. So let me just, yeah, the CDF. So this here is, yeah, let's just use Z for this. So this here is the CDF. So this is the probability that my Z is less than little z. This is the integral from negative infinity to z of f of x dx. And what I mean by f of x, I mean 1 over the square root of 2 pi e to the negative x squared over 2 dx. So what do we do to find, for example, what if I want to find the CDF at 0? What am I asking for? Well, I want to find a probability that my standard normal random variable is less than 0. What's the probability that a normally distributed random variable whose mean is 0 and whose standard deviation is 1, what's the probability that that random variable attains a value less than 0? Well, the idea is that you take the integral from negative infinity to 0 of 1 over the square root of 2 pi e to the negative x squared over 2 dx. What does this expression represent? It represents the area underneath the curve to the left of 0. So this is important. This is the area underneath a bell-shaped curve, which is the PDF of the random variable z to the left. So this idea of left and right is going to be important. So it's to the left. To the left. In particular, of 0. Yes, and so people say 1/2. Very good. Now, how do you know that? How do you know that this area here is a half? Well, we proved already that this area underneath the entire curve is 1. That's right, Alexandra. The whole thing is 1. And that's for every normal random variable. It doesn't have to be just standard. Every normal random variable, we proved it already. We showed it that when we take the integral here is 1. What does this mean? The area underneath the entire random variable, the entire PDF of the random variable is 1. So 0, because of the symmetry, because of the symmetric nature of this graph about the value 0, then to the left of 0, the area will be half of the entire thing, which is 1. That's one way. We know that this will equal 1/2 or 0.5. Now, what happens when I say what's the CDF at 1? What's the probability that my z value is less than 1? Well, it's the integral from -infinity to 1 of 1 over the square root of 2 pi e to the negative x squared over 2 dx, and so on. This is the area underneath the bell-shaped curve to the left, right? This is what I'm finding. I'm finding the area underneath PDF of z to the left of 1. Now, what would that be? What would this probability be? Well, I'm not going to actually do all of that. I'm not going to actually integrate this. And of course, I can't eyeball it, right? I can't eyeball the way I was able to eyeball it using just half of the entire thing. I can't eyeball this. I need to find the area to the left of 1 of the entire curve, underneath the entire curve to the left. So what do we do? Well, I'll show you two things. One way we can do this is use the table. And sometimes they're called z-scores. The table of z-scores, right? And I showed that to you the end of last lecture, and it's also in your textbook. So the way we look at this chart here, this table, as you see here, this is the area under the standard normal curve to the left of the value x. So when we use this table, we have these numbers on this column and in this first row. These numbers here are the numbers for the x value, or in this case, they should have used the z, but it's okay. The z normal random variable, the standard normal random variable. So this is going to be, so for example, if I want to find the area underneath the curve to the left of 0, well, I look at 0.0, 0.00. So these numbers here are the hundredths place, and this gives me until the 10th place. So you put this together, 0, 0, it's 0, 0. And the area to the left of that 0 is 0.5, which is what we already established. Now I want to find the area to the left of 1, just 1.00. So I have to look at this row and then under this column. And the number that is associated with it, it's 0.8413. Very good, Saring. So that's going to be my 0.08413, right? This is the area underneath the curve It's the area underneath the PDF of the normal random variable to the left of 1. This is the area, exactly, well, approximately. But this also represents what? It represents the probability that my normal random variable may attain a value less than 1. That's the probability. It's 0.8413. Or in other words, 84% of the time, the normal random variable will be less than 1. That's what this number means. So always understand the significance in its, as full as possible. So not only is it the area, it's also probability. Not only is it probability, it's also the area. So you have to be able to understand the full scope of what this number means. So that's one way. The second way that I want to show you is using your calculator. And your calculator will be much more precise with the approximation than the table. The table only uses 4 decimal places. But of course, this is just an approximated, it's actually a truncated actual value. So let's see how we can use our calculator to help us out in this regard. So if you have your TI-84, TI-83, it should work out. So when you have your TI-84, okay, so you go to, yeah. So you go to second vars for distributions. Remember, we used, as you can see, these names now, hopefully they start to become more familiar. Binom, we use it for binom CDF, binom PDF. There's inverse binom, there's Poisson, there's geometric, there's chi-squared, and all these other ones. But the ones that we're interested in for this particular one is the normal. And we're going to look at the normal CDF. So when we press the normal CDF, look what happens. Okay, so I'm trying to figure out what is the area underneath the normal random variable, the standard normal random variable curve to the left of 1. So what's nice about this is the calculator gives us parameters that we have to fill out. So the lower is referring to what is the lower bound, right? And you can think of it from the integration perspective. What's the lower bound of the integration? It's negative infinity. Now, how would I write negative infinity here? We don't have an infinity symbol. So instead, we're going to write it as a really, really negative number. And it automatically does it for us, but we can change the lower no matter to something else. But for now, we can leave that. What does this mean, though? This E here means 10 raised to the 99th power. So I'm taking -1 times 10 to the 99th power, which is an extremely large in absolute value, but it's a really negative number, which will indicate negative infinity. Now, what's the upper integration bound, or what's the upper number that we're dealing with? It's 1. We want everything up until 1. So negative infinity all the way up until 1. And what's nice about this is it doesn't have to be standard normal. So with your calculator, it kind of makes the table obsolete. But I still want you to know how to use the table regardless. But then we can specify the mean and the standard deviation. So we are already under the standard normal distribution. So we're going to be assuming that the mean is 0 and the standard deviation is 1. So once we have that all together, we paste, and look what it gives us. It gives us many more, it gives us at least 5 or 6 more digits after the decimal place. So it's 0.8413447404 ... So that's what the calculator gives us. It gives us a more precise number. Okay, so we can use our calculators to help us find the area underneath the curve, which is also the probability. Okay, so any questions about using the calculator? Does everybody follow? Yes, okay, great. Okay, good. So now that that's clear, what if I want to find the probability that my z value is bigger than 2? So how do I find, and then also just go back to the graph. Always go back to the graph, the standard normal bell curve. So we know what it always looks like: 0, 1, -1, 2, 3, -2, -3. So I want to find this area. What I'm saying here is I want to find the area to the right. So this is the area underneath a normal curve, standard normal curve, to the right of 2. Now, what's the idea? How do I find this? The whole table is predicated on the fact that the area is to the left. But sometimes I want to find the area to the right. You can find a complement and plug into the calculator, or you can do, so I'm going to show you both ways. So one way is, well, if I know how to find the left area by the table, so by the table, so using table, I can find the area to the left and then subtract that from 1. Why from 1? Because the entire thing is 1. So to find this piece, I can do the entire thing minus the other side, and that difference will give me the right. So this is the same as saying 1 minus the probability that z is less than 2, which is the same thing as saying 1 minus the integral from -infinity to 1, pardon me, to 2 of f of x dx, which is the PDF, right? So then we can go to our table and look at where 2 is. And I want 2.00, right? I want 2. So this is 0.9772. And when you subtract 1 minus 0.9772, you get 0.0228. So 0.0228. So this would be the probability that my z value will be bigger than 2. And I use the fact that the area to the left of 2 was 0.9772 by using the table and subtracting 1 from it. And I get that. Now, when you use your calculator, you don't need to talk about the complement, however. There's no need for that. You can straight up find it. So using the calculator. So all I have to do is be aware of my parameters. So I want to find the area to the right. So what do? I go to my calculator and I use the same function. I go to second vars, which is a distribution function, and I got normal CDF. So press enter. Now, what's my lower bound? I don't have to do the complement anymore. What would be my lower bound for my calculator? Right, it would be 2. And then what would be my upper bound? 99999, as big as you want, right? So then what we're going to do is we're going to just do the same thing that we had for the negative infinity symbol, we used 1e to the 99, but now instead of being negative, it's going to be positive. So it's going to be 1, and I just have to press E. And so E is second, the blue second J, which is, or the comma here. So second E, that represents 10 to the, and all I have to put is 99. So this number, what I wrote here literally just means 10 to the 99th power, which is a humongous number. And mean is 0, and sigma is 1. So you press paste, and when you paste it, look what I get. I get 0.002275. So I get the similar 0.0022750062. So rounded, if I round this to the nearest to the 4 decimal place, it would be 0.0228. You round up. But do you see how this is a bit more precise? So especially in your homework, I think there's certain answers, and they want it to be a bit more precise than just 1 decimal place or 2 decimal places. So make sure you use your calculator in addition to your table, just to make sure that everything coincides and is okay with the answers. Okay, so any questions about finding the area to the right? So we can find the area to the left, we can find the area to the right using the table or using your calculator. How did you do to the power up? Not exactly sure. Well, you don't have to write, you can write, so you can write this in 2 ways. You can write this as 10 to the 99th power, or you can just write this as 1 second, that little comma button here, and write 99. Those two things that I just wrote are equivalent. They're the same. So the calculator interprets it the same way. So E to the 99, E, and just write 99 represents 10 raised to the 99th power instead of writing it out. Okay? No problem. Great. Great. So here we have 2 ways to find the probability. Great. And now, what if I want to find, so the other variation of all of this is, what if I want to find the probability, for example, of negative 1 point, you know what, let's do this. What if I want to find 0.65, and my z value, my standard normal random variable is between this z and 1.72. What if I want to find a probability that my standard normal random variable is between these two values? What would this represent geometrically? It would be the area underneath standard normal curve between the values of 0.65 and 1.72. So how would we do this? What would this be represented by in terms of the integral? It would be the integral from 0.65 to 1.72 of my PDF. So if I want to use the table, using the table, what am I actually doing using table? How would you find this? So it's 0, 1, 2, right? And so 0.65 is somewhere here, and 1.72 is somewhere here. So what do I want to find? I want to find this area here. And Alexandra, you're right on the money. So since using the table, the area is only to the left, I can do is find the area to the left of 1.72, which would be all of this, and then subtract off the area to the left of 0.65. So that's the big idea here. And when I do that, when I subtract those two areas to the left of 1.72 and all the area to the left of 0.65, the remaining difference would be the area between them. So then let's do that. What is 1.72? What is the area to the left of 1.72 using the table? So 1.7 and then 0.2. This 2 here would indicate it would be 0.9573. So the area would be 0.9573. Subtract that with the area to the left of 0.65. So 0.6, 0.5, go across, go to the bottom, go below, and I got 0.7422. So that's going to be my area. 0.7422, right? 7422. And then when you use your calculator or you subtract it by hand, you get 0.9573 minus 0.7422, and the area would be 0.2151. Okay? So that's the area between the values of 0.65 and 1.72. That's the area underneath. The curve, which would also represents the probability. It represents the probability that my normally distributed standard normal random variable attains values between these two values. Okay, and let's also do number 2, which is using the calculator. And I hope you start to see how useful the calculator is in this regard with finding the area. So now what would be my lower bound for this problem? It will be the smaller number, right? It will be 0.65. My upper bound would be 1.72. And I'll keep the mean value being 0 and the standard deviation being 1. So when I paste this, I get pretty close to the actual number we found, right? I get 0.2151298.587. So of course, this is a bit more precise. Any questions about this? How would you use a chart if the number is negative? Excellent question. Right? That's exactly what you should be thinking. Wait, so I know I get that scenario, I get that scenario, but what about this scenario? What if I have a, so let's think about that. So what if my Z value is less than negative 2.83? So again, drawing this out helps, okay? Having a visualization of what you're finding helps a lot. So this is 0, this is -1, this is -2, this is -3. So negative 2.83 is somewhere close to -3. So I want to find negative 2.83. I want to find this. I want to find this area. And now what's the issue? The issue is that the values for the standard normal random variable are all positive. These are all positive. These are all positive. But I want to find the probability or the area underneath the curve when the z value is less than a negative number. And how would I do that? Does anybody have any ideas as to how we would find this using the table? It's the same symmetry, just negative. Okay, so because it's symmetric, this problem that I'm asking to find is equivalent to finding the area to the right of positive 2.83. So this is the same as the probability that my z value is bigger than positive 2.83. Do you agree? Is everybody in agreement with this? It's the same. So I can find the area to the left of this by reformulating the question as what's the area to the right of this value? It's symmetric, so it should be the same. But don't we know how to treat this? Don't we know how to take care of this? When we have a area to the right of a positive z value, what would that be? This would be what? 1 minus the probability to the left of 2.83. Does that make sense? So then, what is the area to the left of 2.83? So 2.8, and then we got what? 0.3 is over here, so it's the fourth column. So 2.8 with the fourth number here. So it's 0.9977. So this will be 0.9977. Subtract it. Subtract this. So it will be 1 minus 0.9977. So this would be 0.0023. So that would be the area to the left of negative 2.83 because I found the area to the right of positive 2.83, which is equivalent to the area to the left of negative 2.83 due to its symmetric nature, which is beautiful, which is nice. I like this. This is expected because of the symmetry behind this curve. Okay? So this is one using the table. But of course, using your calculator. How to use your calculator for this? Well, your calculator makes this a bit easier now. So I want to find the area to the left, right, of negative 2.83. So my lower bound would be negative infinity, negative 1 second e. Sorry, I should put a 1. Even though I don't think it should matter because it's just 1. So E99. And the upper bound will be negative 2.83. The mean is the same. The standard deviation is the same. Press enter. And look what I get. I get 0.0023274629. It's a bit more precise. A lot more precise than using the table. Okay. So any questions about finding negatives? The values for negative values of z. It's just the same thing on the other side. You just have to flip. Understand that this area here is the same as this area to the right, which is 1 minus area to the left. So all of these different techniques that we've learned throughout the different scenarios of z values are found here. Okay, any questions? Are we all good with this? Yes, 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 yes. Okay. Great. So now that we're more comfortable now with the standard normal, and for standard normal random variables is less than or equal to the same as less than. It is. It is. It at the at with continuous random variables, less than or equal to, and less than are equivalent. Uh, why is that? Why is that? Because again, we're dealing with the area. So if we're including negative 2.3, if I were to say including negative 2.83, I'm including a strip of a line that the area of this line here, if you draw this, would be dimensionless. It would be just zero. And we talked about this, right? In the world of probability, if I were to find what's the probability that my z value is equal to negative 2.83, this is the same thing as finding the area between negative 2.83 and negative 2.83 of f of x dx. But that's zero because the bounds of integration are the same. So because of that, it's almost like, in a sense, it's almost irrelevant whether or not this is equal to or not equal to. The important thing is really the more important thing is the where the less than or equal to or the greater than sign are. What does normal PDF do? Yeah, there's another function here, right, on the calculator, normal PDF. Um, I believe this actually gives you the value of the PDF. So when you look at the PDF again, when you look at the PDF of the standard normal random variable, this one here, it's a function. So you can actually compute the the PDF. So it gives us the PDF gives us the point on the graph. We are dealing with the PDF, but in particular, Daisy, in particular, we're dealing with the area underneath the PDF. The PDF, think of it as just a function. And what we care about more than the function itself is the area underneath it, because we can interpret it utilizing the idea of probability. We're interpreting the area underneath the PDF as the probability that your value of the random variable is within a particular interval. Because in the world of continuous random variables, the probability of a random variable equaling a single number is zero by the very definition of the the world of probability in this idea of continuous random variables. So the normal PDF, yeah, if you use the function in the calculator, that will give you the exact value for the x value that you're looking at. So if I plugged in 2, if I want to find the probability, the function at 2, I'm literally finding what the y value is. That's what that number gives me. I'm finding what the function is defined at the value 2. But at this time, it's not that significant for us, because for now we really just want to understand the CDF, because that gives us the understanding of what the probability of that random variable would be in a given interval. That's more significant than finding the particular one single value of that random variable. So for now, all we care about is the integration aspect of it, which would be the area underneath the curve to the left, whether it be to the right, in between two values, it doesn't matter. As long as we're able to find the area and interpret the area, we're good, and we're in good shape. Okay. Okay. So So now we're gonna get into assume we're gonna get into more word problems related to normal random variables, right? So assume that a person's height um, is normally distributed. Not a person's height, but a group of people is normally distributed with mean of 69 centimeters, and the standard deviation is let's see, no, sorry, not 69 centimeters, 69 inches, and let's make this 2.9 inches. Okay, so we're assuming that the group's height is normally distributed. So the moment you see this, the group's height is normally distributed, this is going to be your standard norm. This is going to be your normal random variable. I'm going to call it X. Okay. So X is going to represent a group of people's height, which is normally distributed. So what does that look like as a PDF again? Normal curve. So my mean here is 69, and I'm going to add 2.9 to that, and that will give me 71.9, and then so on and so forth, right? So then I add this. This would be what, 73.8, and so on. Do it one more time. This would be 75.7, and then I'm gonna subtract this, right? So 69 minus 2.9, so 66.1, and then subtract it one more time. You get 63.2, and then subtract it one more time. You get 60.3. Okay, so this is the PDF. Again, the normal curve, the normal curve for X. Now, suppose I want 74.8. I think you may be right. So let me 69 plus 2.9. Yeah, 74.8. Yeah, so 74.8. And so this is 74.8. Thank you. 74.8, and this will be 77.7. Okay, so this is the mean, okay? This is the mean. And then this is one standard deviation from the mean, mu plus sigma. This is one standard deviation from the mean to the left, so mu minus sigma. This is going to be mu plus 2 sigma, mu plus 3 sigma, so on, right? So what if I want to find a probability that one randomly selected person has a height less than 80 inches. No, sorry, that's too much. What if I want to find less than 70, let's make it 72 inches. So what is it that I want to find? How do I interpret this? I want to find a probability that my X value is what? Less than 72. That's what I want to find. Now, how would I do that? Only using the table. How would I do that using the table? Well, remember, the table is only utilized when you have a standard normal. Standard. This is not standard normal. This is just normal. Standard normal is, remember, when the mean is 0. But my mean here is 69. So what's the idea? The idea is I want to make this, I convert X into Z. What is Z? Standard normal. How do I go from X being a normal random variable to Z being a standard normal? So the idea is that I take X, I subtract it from the mean, divide it by the standard deviation. And you can check for yourself. If I find the expected value of Z, I would find the expected value of X minus mu over sigma. But what is the expected value of this? Remember, I can take out the 1 over sigma, and then multiply it by the expected value of X minus mu. And then I can, because of the linear properties, I can write this as expected value of X minus the expected value of mu, which is just mu. But what's the expected value of the value X? What is the expected value of X minus mu? Isn't mu the expected value of X? So aren't I subtracting the same thing? So isn't this going to be 0? So this new random variable based upon the original random variable is my standard normal. This is my standard normal. And you can do the same thing here with in terms of the variance, right? What's the variance of Z? Well, isn't this the variance of X minus mu over sigma? And remember when you add or subtract a constant, it doesn't affect it. So this is the same thing as saying the variance of X over sigma. But when you take out a constant, which is what sigma is, right? This becomes 1 over sigma squared. And the variance of X is sigma squared because the standard deviation is sigma. So this equals 1. The variance of Z is 1, which indicates that the standard deviation of Z is also 1. So does everybody follow this? Does everybody see why I want to do this to every random variable? Every normal random variable to make it standard, I take the random variable, subtract it by the mean, and divide it by the standard deviation. And in doing so, I take this curve and reduce it to the standard normal curve. So the idea is that once I'm able to do that, I can write it this way. I can write X, I can subtract it by mu, but of course, whatever I do on one side of the inequality, I do it to the other. I do 72 subtracted by mu, divided by sigma, divided by sigma. Now this here becomes z. I'm just reformulating the problem. So the problem that my random variable is less than 72, I want to find a probability for that. I want to find the area underneath it, right? I want to find the area underneath the curve to the left of 72. This problem that I originally have is reformulated to find a probability that my z value for my standard normal, for my standard normal random variable is less than what? So what is 72? So what is this going to be equal to? Well, it's 72 minus mu. What is mu? 69. And then what's my standard normal? I mean, my standard deviation is 2.9. So when I do this, this becomes 3 over 2.9. So 3 over 2.9 is 1.03. I'm just writing it as 1.03. 1.03. So this is equivalent to doing 1.03. Do you guys see that? Does everybody follow this? Any questions about this? Because this is pretty crucial. Yes. Need to review the purple. Yes. You can check this on your own. You can check this. The reason all of this is showing is the reason as to why when I rewrite my function, when I write x in this way, I have what's called the standard normal random variable. So you can check this as to why the expected value will be 0 and why the variance will be 1, which will indicate the standard deviation is 1. So I just created a random variable whose mean is 0 and whose standard deviation is 1, which would indicate that my random variable is a standard normal random variable. And this is the formula for every random variable x. So for every random variable x, I can rewrite it as a function that represents the standard normal. And now this problem here is reformulated to this problem here, and we know how to use the table for that, right? We go to our table and we want to find the area to the left of 1.03. So 1.03, so we got 1.0 here and 0.03. So it's 0.8485. So 0.8485. Okay, so that's the answer. That's my probability. I found it. The probability that the one randomly selected person has a height less than 72 inches, it's 0.8485. Now, what if I use my calculator instead? So this is why the calculator is very powerful, because now I'm going to use the normal vars CDF. My lower bound here is negative infinity. My upper bound here, I'm going to put 72. My mean is what? 69. And my standard deviation is what? 2.9. And when I press this, look what I get. I get pretty much very close. Not exactly, right? But very close. 0.849544. Of course, there's more likelihood of some round off error now. Because this itself, you see, this itself was rounded. This is 1.0344, blah, 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 blah. So even this was rounded. So this would be also rounded. But do you see how we can use our calculator to find that value? Okay. So these aren't necessarily quite the same, but it's in the same ballpark. With the calculator, I don't have to consider this. I don't have to consider this idea of making it into a normal random variable, but using the table, I do. Using the table, I do have to think about the standard normal and how I get there. Okay. Okay. Now, now that we're able to do that, um, now I want to go do the opposite of what we've been doing so far. So what do I mean by that? So this is the idea of percentiles. So remember when you score in the, for example, if I were to say I scored in the 99th percentile in a standardized test, that means I scored quote unquote better than 99% of the people who took it. Or if I scored in the 85th percentile, I scored 85% better, right? So then what I want to be able to do now is find which height is the cutoff to be in the quote unquote 75th percentile. Within this group of people. So what do I mean by that? Now let's look at the curve again. Um, this was what, 69? And then we had 71.9 and 74.8, 77.7, so on and so forth, right? We had the other side as well. So the 75th percentile, well, first of all, what is the 50th percentile? It's halfway, right? So 50th percentile is associated with which number? With the mean. Does everybody see that? Because 50%, which is 0.5, is the area to the left of 69. So the 50th percentile is smack dab in the middle, which would be represented by the mean. Okay. But I want to find the 75th percentile. So I want to find, what do I want to find? I want to find this. What is this value here whose area is 0.75? This represents 75th percentile. I scored 75% of the time better than, or in this case, I had 75%. I am taller than 75% of the people in the group. So in reality, this is what I'm trying to figure out. I'm given the area and I want to find that X value. So X is bigger than some value of X. This is less than some value of X, which equals 0.75. So normally what have we been doing up to this point? We were given the X value or the Z value, and we found the area to the left. Now we're given the area to the left by the percentile, this idea of percentile. We're given the area to the left, and I want to find what is that X value associated with that area to the left. Does everybody follow? Yes. Okay. Because of the idea of that I can go from the normal random variable to a standard normal random variable and vice versa, this is equivalent to saying what is the Z value associated with 0.75. It's equivalent. So I'm going to use the table for this, okay? So the first thing is I'm going to use table. So I have to go back to my table, and instead of using the rows and columns of the values of Z, right? Instead of these, I have to now go back. I have to go and go into this world and see where is 0.75 closest to. So it looks like 0.75, you see here, is like an in-between number here. 0.75 happens somewhere in between. In between which two numbers? 0.6, 0.67, and 0.68. So it looks like this z value would be what? What would be the z value? Less than 0.675. I'm just going to average it out, right? Does that make sense? Now, go back to this idea that x and z, how are x and z related? Well, z is equal to what? X minus mu over sigma. And what if I want to solve for x now? What would x be? X would be, if you solve for it, it would be mu plus z times sigma. I know what mu is, 69. I know what the z value is. This is my z value, is 0.675. And I know what the standard deviation is 2.9. So when I actually compute this, I get 69 plus 0.675 multiplied by 2.9. And I get 70.9575. Make sense? So what did I just find? I found that the x value, that the height for the cutoff of being in the 75th percentile is being 70.9 inches tall. Oh, literally treat this as an algebra problem, as a literal equation, and you're solving for x in terms of all the other constants and variables. So then you would multiply both sides by sigma, right? And then you would add by mu. So then x is equal to mu plus z times sigma. And I know what sigma is. I know what mu is. That's what the x value, the x random variable comes with. And z is what I found here. Z is what I found based upon the table. I used the table to figure out what that z value is. And then I mapped that z value to that random variable that we started with. So we're going to be going from random variable to standard normal, and it's from standard normal to random variable. So we have to be able to make that connection now. Okay. And the nice thing is we can actually do that as well with our calculators. So if you go to your calculator, you go to the second bars again, but we're not going to use normal CDF anymore. We're going to use inverse norm. So the area, you see here, the area there's, and then you have to be careful with this. The area here, we're gonna write it as 0.75. The mu is the mean, which is 69. And the standard deviation here is 2.9. Now, the important thing is the tail. What do we mean by the tail? We're saying, where is this area pointing towards? Is it pointing towards the left? Is it centered, or is it to the right? Well, we're treating 0.75 to the left, so we're going to keep it as the left. And so let's see what happens when you give us the answer here. Do you see we get 70.956, which is pretty close to what we got. We got 70.9575. This is, of course, the calculator gives you a more precise number because we estimated that z value. But again, the important thing is, what does this number represent? This is the x value, or the value of the random variable associated with the area being 0.75 to the left, or in this case, saying that if you're 70.9 inches tall, you're in the 75th percentile of all the people within this group in terms of the heights. Okay, does that make sense? So the inverse norm.